final round key, and that's the end. Right? And out comes the 128-bit block of total gibberish. This can be
on hash and Mac.
like that. Right, so we'll bring the diagram back, and with that in mind, we will talk about what each of these does. Substitute bytes, that's our substitution box, is literally a lookup table. It's a cleverly designed lookup table. They haven't just made this up. Each byte is mapped to a different byte based on a function in this field. But most importantly, there's a few things that they've done to try and design it to be as complicated as possible. Right? So it's very non-linear. So it's very difficult to kind of represent this as a mathematical function, exactly what it is that it does. In fact, let's just do one and then we can see, right? So we've got our grid. Let's put this here. We've got our grid, which I've now drawn many times. This is B0, this is B1, all the way up to B15. Now, what we're going to do is we're going to take this byte, we're going to look it up in our table, and we're going to replace it with a different one. One, right? So our substituted byte, like that. And we're going to do that individually for each of these. To make this, what we're going to do, this is B0, this is B1, all the way up to B15. Now, what we're going to do is we're going to take this byte, we're going to look it up in our table, and we're going to replace it with a different one. Right? So our substituted byte, like that. And we're going to do that individually for each of these. To make this function more confusing, it's been designed such that there are no fixed points. That means no byte is substituted with itself, so you don't start with a 15 and end up with a 15. And there are no opposite fixed points, which means all the bits flip. So for example, the opposite of 1010 would be 0101, right? And this is for a whole byte. They don't exist in this, it's been designed that way. So this substitution box is really quite powerful. And it's one of the reasons why this is a really good algorithm. As it happens also, it's just a lookup table, so it's nice and quick. That's the first thing. So we've substituted our bytes. We've taken our plain text, we put in part of our round key, or this is our initial key, and then at the beginning of the round we'll make some byte substitutions using our SBox. Then we're going to shift the rows. This is really straightforward. So we're just going to take the first row and do nothing to it. We're going to take the second row and we're going to move it 1 to the left. So B1 goes all the way back over to here. Right, so they wrap around. This moves this way, and this moves this way. And this moves this way, and this obviously goes to the end. This row moves 2, so this goes to here, this goes to here, this goes round back to here, and so on. And this moves 3, right, which is another way of saying it moves that way. But you know, so this one goes all the way over to here, this one goes over to here, and so on. Remember, this is going to be an iterative process, and what we want to do is move these things around and permute them. So if this is our data path with our columns, by sharing bytes around the different columns, when we combine it with the mixed column step, which we'll do in a minute, you'll see that actually we're mixing everything up. So within just a couple of rounds, everything is very, very jumbled up, and that's obviously a really good thing because it's going to be much, much harder to break. Right, so we're just taking bytes and we're putting them in a different place in this grid. So that brings us to mixed columns, which goes along with this. Right? So now that we've moved things into different columns, what we're going to do is we're going to take this column here and we're going to mix these right up. We're going to take this column and mix these right up, and this one separately. So this is a column-wise operation. So this byte has gone over to here and then been mixed into this column. This one has gone over to here and been mixed into this column. So these two operations together are, you know, they're doing a good job of jumbling everything up. Right, would be my technical way of putting it. This is going to be done using a matrix multiplication. So let's just turn it off. I'm going through a lot of your paper today. For some column, let's say C0, C1, C2, C3, we're going to multiply it as a vector by a matrix. Right? Now, we've dealt with matrix multiplications occasionally in computer file. We're not going to spend too much time talking about it now. But this matrix is 2, 3, 1, 1, 1, 2, 3, 1, 1, 1, 2, 3, and 3, 1, 1, 2. Now these numbers, they're big enough and jumbled enough that something interesting happens here, but they're small enough that this is quite fast. right, on hardware implementations and things like this. If this was 50, it made your algorithm slower. So if you remember from sort of linear algebra, a matrix multiplication is going to produce another vector out, so it's going to replace this column with another one, and it's going to be a combination of all of these. So this one times this one, plus this one times this one, plus this one times this one, plus this one times this one, and then we repeat this process for each of the values. So we're taking bits and bytes from all of these in this column, jumbling them up, moving them around, shifting them. And there is a reverse inverse matrix that does the exact opposite when you want to decrypt as well. So although this is doing a good job of jumbling everything up, we can actually also undo it. The only thing to mention, of course, is this is not a normal multiplication in the sense that we're inside this finite field. So our add operation is an XOR, and our multiplication operation is a multiplication inside this finite field, right? Which is modulo a polynomial, and you know we'll sort of leave that for someone to look into. Although we'll talk about it in some extra bits. So I guess like once more from the top, we take our plain text and we XOR it with the first part of our expanded key, and then we're going to repeat this process over and over again. So we're going to substitute some bytes using our nicely designed S box. We're going to shift the rows along, and then we're going to mix all the columns up. So we're going to substitute and then permute our data in this grid. Then each time we're going to add the round key, which in this case is XOR, and then we're going to repeat this process, except for the last round where we don't bother to mix the columns because it doesn't really help us. And then at the end we add in our final round key, and that's the end. Right? And out comes the 128-bit block of total gibberish. This can be described as kind of a random permutation. That is to say, it takes some input and it performs what appears to be complete randomly producing an output, when in fact actually obviously it's had quite a lot to do with this key. If you have the key, you can then undo it. Each of these steps has an exact opposite step that we can go back up through to undo this whole process.
Does this ever go wrong?
You mean, how so?
Well, it just seems to be so many stages and so many parts to it.
So that's a very good question, because I guess there's two answers to that question. One is technically no, because they have what we would call test vectors, which are, this is all zeros. When you put this in with this key, this is what you should get. So you can test your algorithm quite a lot before you would put it into production. But in terms of sort of security issues, actually yes, right? So if you get this implementation wrong, you can kind of undermine the security of this whole cipher. There have been things like cache timing attacks and side channel attacks where bits of key have been leaked because people have not given due care to how this is implemented. One of the neat things about AES is because it's a standard, it's now in CPU hardware. So there are AES instructions to perform one round, to perform a final round and things on an Intel and an AMD chip and on others, and they are impervious to these kind of attacks, and they're also ridiculously fast. So if you're using AES on a well-equipped CPU with the right instructions, we can be talking gigabits per second of encryption, which is, pretty good. So that's why something like BitLocker or some kind of on-disk encryption, you won't notice it. You click a file and it's already decrypted it and shown it to you before you can sort of realize what's happened. And it's because of the speed of this kind of stuff. Well, perhaps we'll talk a little bit more about Galois fields, because.
And so AES has three main subroutines. So the first subroutine is, which is called in the technical language layers. So the first is the byte substitution layer, or called SBox, this one. So we're going to see briefly how it works. But the idea is that with SBox, you provide confusion. So you obscure the connection between the ciphertext and the key. Then the second layer or subroutine is the diffusion layer, which by definition, it says that provide diffusion, so a single change on the bit on the plain text then statistically causes half of the bits in the ciphertext to be changed. And the third layer is called the key addition layer, which is just an update, an XOR to update the state of the encryption, because we execute several rounds of these three layers. So we're going to see this. So just what I want to say here is that we have 16 blocks or 16 states, because we are focusing on IS 128 and bits. So this means that we are using 16 bytes. So each of these states, which is a byte, 1 byte, okay, 8-bit. If you prefer to see an algorithm definition of AES, I've written the algorithm definition. It's the same as we said before. With the key schedule, just put at the beginning instead of the end. So we have 10 rounds in which we do the Xbox. Then we do the diffusion layer, which consists of shift rows and mixed columns. And then we have, sorry, this is the key schedule, is another thing. So the key schedule is a way to expand the key that is going to be used on each round. So since we have the key of 128 bits, we want to use different keys on each round. This key schedule generates different key from the original key of the equal size. And then there is the key addition layer at the end. So actually you can have a comparison between the graphical picture of AES that you find on the book with this algorithmic definition of the same cipher. So another thing I forgot to say is that the 16 states can be represented as a matrix, and the standard representation is that you represent by a column. So this one, sorry, no, yes, 001, this way, by column. Okay, so now what we're going to do is just have a look at how this box is implemented and how the diffusion layer is implemented, and then how the key addition layer is implemented. The goal is not to recall exactly the steps, it's just to recall the idea behind each of these subroutines or layer. So the byte substitution layer or S-box has three properties. So the first is that it uses a fixed S-box. So this means that this table is fixed for any encryption that you are going to use with AES. It's public, so the attacker knows this. So what happened here? What happened here is that when you have an input on your current state like this, so for instance, the first is EA, then I look at my S-box, so EA 87, and I just replace the original value with the value that I found on this lookup in this table. Very easy. But what are the properties that this table has? So first is it identical. So you use always this S-box for each round. You don't change it. Second, the most important, it is nonlinear. So it means that if you try to add any two S-boxes, so let's say A5, which is 06, and A6, which is 24. So now, if you add this, you don't get the sum of the, you don't get as a result the sum of of the original column and row. So the sum of two S boxes is not equal to the sum of two different S boxes, not equal to the sum of the same cell. Okay, I think that's the formula says much better than what I'm saying in my speech. Okay, so but nonlinearity means this addition is not equal to this addition, and this is extremely important for confusion. So as you can say, I cannot tell you already, so it's very confusing. But jokes apart, nonlinearity is the property that provides confusion. Because if the attacker sees any any ciphertext produced by a S-box, it's very hard to use cryptanalysis to go back and see what was the original S-box. The original element that produced that particular value. And the third property is that it is bijective, so means that exists only one mapping of the input to the output. And this means that when I try to decrypt, I will be sure that the element that I'm choosing with reversing is that element. So there is no ambiguity on which cell I should choose when I get a value. So take away from this box, it provides confusion. It uses the S box is public, is it identical for each round, and the nonlinearity is the key property that provides confusion. And since it's implemented as a lookup table, it's very efficient. Questions? Okay. So the second step is provide diffusion. And diffusion is we use two subroutines, shift rows and mix columns. Shift rows is just a permutation of the data. So as you can see, the first row is not shifted. The second row is shifted once to the left. So look at S11 is now here, and S01 is now at the right part. Then the third line is shifted twice. 02 was here, now it's here, so twice to the left. And the fourth row is shifted 3 times to the left. Okay, this is extremely straightforward. But as you so this is very intuitive because we are trying to have diffusion. So we want to scramble the bits and expand the bits in output in order that if I have a change in the 1 bit in the input, then I have statistically half of the bits shifted in the output. And what we do, and this is linear, okay? So we don't have confusion anymore. So if we sum the values of 2 different shift rows, to different values, then this is equal to shifting the sum of these 2 values. This time I said it better. And when we do mixed columns, is exactly the same thing as shift rows. So at this time we shift the columns instead of the rows, and this can be done by matrix multiplication. So this element multiplied with a fixed matrix get a mix of the columns. Questions about diffusion layer? So we are not changing the values, but we are just moving within the same matrix. And the last matrix. And the last step is the key addition layer. So I do an always good XOR, and this is just, I have my key 128-bit, so meaning 16 bytes. Each of the key is 8-bit, each element of the state is 8-bit, then I XOR each element of the current state with a corresponding element of the key, and then I get the new state. So just to resume the resume the three layers of AES: S-box to provide confusion, shift rows and mixed column to provide diffusion, and key addition layer to protect against inverting attack, because now that I see the states and I don't know the key, I cannot get back to the previous state. So actually this S, you can see this was S, this is S prime. And from S prime, I cannot go back to S, so I cannot do the decryption if I don't know the key, if I don't have any clue about the key. Important points. AES, as any other symmetric cipher, is conjectured to be secure, is not proven to be secure. No one can prove any clue about the key. Important points. AES, as any other symmetric cipher, is conjectured to be secure. It's not proven to be secure. No one can prove mathematically that a ciphertext is indistinguishable from a pseudo-random permutation. The only way which we can do is do cryptanalysis. So test, trying to do differential cryptanalysis or linear cryptanalysis, well-known approaches in order to break symmetric cryptography. When we will do asymmetric cryptography instead, we don't have anymore the same definition as pseudo-random permutation, and in that case we will have proof, meaning that if I have some mathematical assumption, then I'm ensured that no one can break that ciphertext with a polynomial limited attacker. So this is something that you will do in security too if you choose the security specialization in your master. So this is the difference between symmetric encryption and asymmetric encryption. Symmetric encryption cannot be proved secure mathematically, while asymmetric encryption can. All right, so questions about AES or symmetric crypto? Otherwise, we will move to hash and MAC. Okay. Then, of course, if you have any questions, stop me at any time or use the forum on Learnit. Okay, so let's move on hash.
Well, we did a video on the Feistel Cipher, and hopefully people enjoyed learning about what I think is a really cool method of encryption. Now, I actually wrote some code for this, which we didn't end up putting in the video just because of time, but I did put it on GitHub, and people, as soon as you put things on GitHub, people go, oh, I can contribute to this, which is a great thing. And so we've added some extra modes of operation. So I thought that's what we'd talk about today. When you run a cipher, you don't just run it because it's only got a certain block size. So how do you do that? If you've got a file that's 2 gigabytes, but you've got a 128-bit block, then what do you do then? Right, so we're going to talk about modes of operation. We looked at the Feistel network, which is a symmetric cipher, and it's a block cipher. That means it takes an input of a fixed size and it outputs the same size. That's how block ciphers work, right? They take a fixed block. So that means that unless your message is exactly that length, we're going to have to do something to try and actually use this cipher for encryption, right? So day to day, when you're sending traffic over the network, the chances of it exactly being the right size for an AES block is obviously quite slim. So what is it we do? So we're going to look at 3 different modes that are going to get, I guess, progressively better. Right, we'll start with the rubbish one, but perhaps the most conceptually simple. And then we'll talk a little bit about padding as well, because of course you might have too small a message, and then we've got to think about it. So the first thing we could do is we could just naively say, well, look, let's just split our message into lengths of the right size and then encrypt each block at a time. Right? Now, if we get to a message at the end which is too short, we could pad it in some way. Right? So this is called electronic codebook mode, and it kind of harks back to when there was a literal codebook that you'd flick through to get the codes. So we have our encryption algorithm. So this could be a Feistel network, could be AES, could be something else. And this is going to encrypt using some key. And we're going to put in our message block 1. So that isn't the whole message maybe. That's just the first block of message, the first 128, the first 256 bits, depending on what your message is. And that's going to produce ciphertext 1. Now, we can just repeat this process. So we can go message 2, and then finally message 3, because I've run out of paper again. The good thing is this is trivial to implement, right? If you have a cipher that works on a block, splitting some bytes into blocks, not very difficult. And then the encryption is also quite straightforward. This will have a decryption, so we just go back up this way. So we go message 1, we can encrypt it to ciphertext 1, and then we can decrypt it again back to message block 1. This also has the advantage, but it's quite fast. If you've got maybe 8 cores in your PC, or even more than that, you could do multi-threaded versions of this, where you could be doing these 2 at the same time, and all these ones over here. And so if you're decrypting things, that's going to be quite quick. And finally, if you want something in the middle of a big file, so let's say you're watching a streaming movie and you want to jump halfway through, you can do that because you can jump to whatever message or ciphertext block it is that we want to look at and then encrypt or decrypt it right then and there. So that's quite helpful. So this is electronic codebook, or ECB. Nice as that looks, it's not at all secure and it's terrible. So don't implement it. I've already done that online for you. The problem with ECB is that it gives away just a little bit too much information about our message. Right? So the key thing here is that, assuming for a minute that this block cipher is good, then if we have a message that goes into this ciphertext, we're not going to be able to reverse that if we don't have the key.
and Mac. And the main goal that we want to achieve is integrity, at least for hash functions, but also authenticity with Mac. So you have already seen hash functions in probably introductory programming courses. And you have seen that hash function can be used in different way. In security, we use it a lot, for instance, for virus protection. So if we want to see if a file is a virus, so antivirus just hash this file and see if they have the same hash in their libraries of virus. They can be used for one-time passwords. They can be used to store the passwords. But the most important thing about hash function is that they are themselves a fundamental ingredient for many crypto primitives. which were stated in the early 40s. The first is confusion. So I want that the connection between the ciphertext and the key that produced that ciphertext is as much complicated as and the second principle is diffusion. So this means that if I get my message of plain text and I encrypt with a key and I get a ciphertext, then if I take again the same message, I just flip one bit on the original input, okay? So my message was 001100, and the second message 000111, okay? I just flip the last bit. Now, and then I put the same key. The second ciphertext that now I get is at least statistically flipped of half of its bits. So one bit change on the plain text produce statistically at least half bit change change on the ciphertext. These are the two good principles on having block ciphers. So, questions so far? How the communicating party decide to reuse this? All right. Algorithmically. And I'm telling you how to do this with the best symmetric cipher ever conceived so far, because no one has broken it. It is the most popular, is used anywhere, is used currently probably in this Zoom meeting to encrypt our stream of data. It's called Advanced Encryption Standard. The block length, the message, the plain text is fixed to 128 bits, and the key length can be as top secret. So it means that NSA use AS for sending their document string. If you prefer to see an algorithm definition of AS, so let's look now at AS. So AS has three main subroutines. So the first subroutine is which is called in the technical language layers. So the first is the byte substitution layer, or called S-box, this one. So we're going to see briefly how it works. But the idea is that with S-box, you provide confusion. So you obscure the connection between the ciphertext and the key. Then the second layer of subroutine is the diffusion layer. which by definition, it says that provide diffusion. So a single change on the bit on the plain text then statistically causes half of the bits in the ciphertext to be changed. And the third layer is called the key addition layer, which is just an update, an XOR to update the state of the encryption, because we execute several rounds of these 3 layers. So we're going to see this. So just what I want to say here is that we have 16 blocks or 16 states, because we are focusing on IS 128 and bits. So this means that we are using 16 bytes. So each of these states, which is a byte, 1 byte, okay, 8-bit. If you prefer to see an algorithm definition of AS, I've written the algorithm definition. but it's the same as we said before. With the key schedule just put at the beginning instead of the end. So we have 10 rounds in which we do the X box, then we do the diffusion layer, which consists of shift rows and mixed columns, and then we have sorry, this is the key schedule. Is another thing. So the key schedule is a way to expand the key that is going to be used on each round. So since we have the key of 128 bits, we want to use different keys on each round. This key schedule generates different key from the original key of the equal size. And then there is the key addition layer at the end. So actually you can have